All right, so here we go with chapter 7, sampling and sampling distributions. So hopefully you find it as fascinating and interesting as I do. You're like, I'm betting money. I won't. All right. So a couple things just to introduce the idea, some terms, okay? Uh, I won't read all of them to you, but a couple that really matter to us is a population, which I think we've already covered. It's like every possible data point in an entire group, right? Some populations are huge, like the population, the number of people in the United States. What is that, 320 million, somewhere around there. Population of people on the earth, 7 point something billion. There's a bunch of them. Some populations are small. Like if our population was set to the number of students in this class, that's a pretty small population. Okay. So don't just think because it's a population, it has to be like a giant number. Some populations are small. Okay. And then a sample, which is a subset of a population. Okay. So those are the two. I mean, all the terms, I guess, are good, but those two really matter to us. And going forward, we'll be using those terms a lot. And like, why do we sample? Well, because it's impossible sometimes to measure everything in a population. It's just, I mean, I guess it's not impossible, but it would be so costly, right, to actually interview every person in America to find out their opinion on a topic or something, even if we tried to do it online, because you'd have a bunch of people that didn't answer, you'd have to like chase them down and get them to answer. So it's just so costly to do that, that we take samples. And I like that they put good on this last bullet point in like quotations. With proper sampling methods, sample results can provide good-ish estimates of population characteristics. So that's what this is all about. And this is what gets used a lot in business and politics and everywhere else, is sampling. Okay. So for this chapter, and actually chapters moving forward, remember how like in the last chapters I tried to break it down and be like, here are like the 3 types of things, and here's how you kind of try to recognize each one. So we're going to have 2 types of things that we have to recognize, and then breaking that into 2 different categories. Okay. So the first thing we're concerned about is, are we dealing with what's called a finite population or an infinite population? So a finite population is what it sounds like. It's a population that is small, relatively small. And it's related to, and we'll talk more about the definition in a minute, but it's related to the size of the sample relative to the size of the population. Okay. Whereas an infinite population is a population that's so big that we're probably never going to get a sample that is even close to like, even like 1% of the whole population. You think about 1% of the population of the United States is still 3.2 million people. It would be still costly to gather a sample of that size, right? So we're certainly not going to get a big or sample there. So finite populations are usually things like this, right? Like number of people in the class, or even if you're Walmart, right? And you have a bunch of, they call them SKUs, stock keeping units, the numbers on the barcodes, right? You have a finite number of those. I mean, you can address each one of those. In fact, they have to know exactly what products they have. So when we're dealing with a finite population, we'd say a simple random sample of size n. So sample is always, the size of the sample is little n, okay? And the population size we denotate with a big N, okay? Is a sample selected such that each possible sample has the same probability of being selected, okay? Which, if you think about it, sounds like it should be easy, but sometimes it's actually really hard to make sure it's truly random, to make sure that you're not somehow skewing this by, tilting your thing one way or another, and getting a group of people. For example, if I was like, we want to see who young people are going to vote for. So we're going to take this group of people, we're going to say 18 to 25-year-olds, who are they going to vote for in the next presidential election? And then, because it'd be way easier to collect it, we put it out there online. Well, where did we put it out there online? Did we put it on a website that tends toward more liberal or more conservative people? Are we getting slanted information just because by putting it online, we're getting the type of people who would answer online questionnaires? And is that, it's super hard to get a good sample. But with a finite population, it's usually easier because it's a smaller group of people for the whole population, and therefore you can do something as simple as like just use a random number generator, assign a number to everybody, and then pick the first 20 numbers or whatever. So actually, I was going to show you, Excel has a function for generating random numbers. So here's somebody wanting to look at baseball teams, and so they could just use the random number generator Excel. It would create these random numbers, and then you just sort them and be like the first 5, that's the group we're going to use, or whatever. Okay, so just showing you that. I don't know that we're going to use it a lot, but you can use Excel to generate a random number. It does a truly random process. All right, with an infinite population, though, it becomes even more challenging. So there's actually, I'm trying to remember where it is. There's like this city, and I want to say it's in Wisconsin or like Minnesota, and it has roughly the same demographic makeup, like percentages of population, as the United States as a whole. So it has, like, if you were to average the number, or like, say there's 52% of American population is white and another 26%, or whatever, its city population matches roughly the United States on both gender and race. And so they use it for like a test product place all the time. Like someone's like, is this going to play with the United States as a whole? But I'm like, it's still Wisconsin. And I'm sorry, but like, I don't live like Wisconsin people live, right? She's wearing a jacket because it's 62 degrees outside. Okay, Wisconsin people would be like, oh, it's balmy, right? Like they'd be in Bermuda shorts or something. Because so like if you thought, oh, I'm going to use this test market, but I'm testing like some weather related product, I don't think you get a very good sample. Because how many of you guys own an umbrella? Okay, a couple. Like if you live in San Francisco, you would all own an umbrella. We live somewhere where it doesn't rain. I mean, it does. And then every time it rains, you're like, dang, I should have an umbrella. But then it doesn't induce you to go buy one, because actually it's rained a lot this year, but this is like, I never fix my windshield wiper blades until it's like, oh yeah, because I don't think about it. It just dry rots in the heat. And then, okay. So, okay, I've made my point on sampling. I think it's challenging to find a good random sample. So the most basic type of inference, okay, is what's called a point estimate. And a point estimate, it's like, again, so we get a point. In this case, the mean is a type of point estimate from a sample. So we take the mean of the sample, and we assume then that that's probably close to what the mean in the population would be. Okay, and the larger our sample size, the better that point estimate typically is. The lower the amount of error in that. Okay, so you'll see this terminology. They'll use X bar as the point estimate for the population mean mu. So recognize, if you see this number, or this Greek letter mu, lowercase, that means the population of the mean. I mean, the mean of the population, sorry. Whereas if you see X bar, which is X with a bar above it, that means the mean of the sample. Okay. And you'll see, most of the problems are like word problems, but occasionally, right, you'll see like that one in the last one where it's all done in like mathematical notation, and you're like, oh, I don't know what to do with this. So also recognize that for standard deviation, the point estimator so sample standard deviation is a lowercase s, and for the population standard deviation, it's a uppercase Greek sigma. Okay, or is that a lowercase sigma? I think it's a lowercase sigma. Uppercase is like I don't know all my Greek letters. I know the ones I have to know, right? And then for proportion, which we're going to learn about in this chapter, P bar is the point estimator for, so the sample proportion, and P is the population proportion. Okay, and we'll talk about proportions a little bit more in a minute. So just, I guess I'm just like, be familiar with what these little things mean, because they're going to come up over and over and over. Yeah, X bar, they call it. That's the term, actually. X bar means the sample mean. So these are sample, X bar, S, and P bar. And then these are populations, right? Mu, sigma, and P. Why does proportion not get a Greek letter? Because they suck. No, I don't know why. Like, sorry, we only have so many Greek letters. You don't make the cut. You just get a P. All right. So EAI Corporation have 2,500 employees. We take a simple random sample, probably as simple as like going into Excel and using a random number generator and just choosing 30 people randomly, okay? We're gonna look at their salaries and then whether or not they attended a management training program. So there's all our data. 30 people, 10, 20, 30, annual salary. Doesn't look like a bad place to work. I mean, they're coming in pretty solid in the 70 grands. I don't know about most of you, but at this stage of your life, most of you are probably thinking like 70 grand. That'd be pretty good, right? Unless you're thinking of playing in Major League Baseball, then 70 grand, that's not even league minimum. What is the league minimum in Major League Baseball? Do you know? 150. What is it in pro volleyball? You know where they make big money in volleyball? Like Western Asia, like Saudi Arabia, Turkey. I didn't know, but it's a thing there. Okay. So there you go. Brooklyn's gonna be playing in the Turkish league. What's that? Whoa, you're way off. All right. So to estimate the value of a population parameter, we do, this is a term. Parameter means population, and statistic is talking about a sample. So we would say, like, if we take the mean of the sample, we'll be using the sample statistic mean to estimate the population parameter mean. Okay. In other words, we're using what the sample tells us to make a guess, an inference about the population. All right. So for this little sample, we can see on average, we came up with pretty darn close, right, by using that sample. Because their population only was 2,500 employees, they could just figure out the average, but they came up with 71,814 by doing that sample, and that's pretty close. Standard deviation, pretty close. And then the proportion. So the proportion means, in this case, they were measuring what percentage of the people had completed the management training program. Okay, and they came up with 63% in their sample, and 60% is what the population parameter is. Most of the time, you can't actually do both. Why would you do both, right? If you could measure the population, you just measure it. So we use these inferential statistics because of the cost, time, or energy involved in trying to measure the entire parameter. But I think this is just trying to give us an example of how those things match up. All right. I won't read that to you. I'll leave it up for a few more seconds because you can read, and then I'll move forward. All right. So the process of statistical inference is we have a population with a mean. We take a sample of n elements from that population. The sample data provides us a value for the mean. And then we use the value X bar to make an inference about the population. I mean, I don't know that they needed a flow chart for this, whoever designed the slide, but recognize that's the process you're going through. Honestly, I wouldn't think of it in 4 steps. I would just be like, I took a sample and took the mean of it, and now I'm going to say, I think that means roughly representative. of the population. Good flow chart. All right. So we need to know if we have a finite population or an infinite one. And we're going to define a finite population. Let's see. A finite population is treated as being infinite if little n over big N is less than 0.05. In other words, if the sample is less than 5% of the population, and we're talking about the number in it, okay, then we're going to treat it like an infinite population, which means we're going to, so if we have an infinite population or a finite population that is less than 5% of the, where the sample is less than 5% of the size, then we just move ahead with regular statistical testing. This is why we need to know this. But if our little n, so the number in our sample, is more than 5% of our population, then we have to correct for that fact using something called the finite population correction factor. I love that term because, like, you guys are getting ready to go to Thanksgiving, and if your parents are wondering if they're helping you at all with college, and they're like, is my child learning anything of value? Just bust out that term, finite population correction factor, and they'll be like, oh, this kid's smarter than me, like that. I'm getting value out of their EAC education. Okay. So this is the finite population correction factor. So if we're going to find the standard deviation of X bar, meaning of the sample, right? We're going to say, so here's the formula for standard deviation. So to find the standard, so in an infinite population or a finite population where the n is the big N, I mean the little n over the big N is less than 0.05, there's our formula. For a finite population, this is the correction factor, which is the square root of big N minus little n, so the number in the population minus the number in the sample, divided by the number in the population by 1. So that sounds like a lot of crazy math. All it means is when we're finding the standard deviation, or when we're finding the other things we're going to talk about in a minute, if our sample is greater than 5% of our population, we have to multiply it by this little correction factor. Square root of big N minus little n divided by big N minus 1. So it sounds scary, but honestly, all you're doing is saying, am I dealing with a finite population? Which means N over big N is greater than or equal to 0.05. That's it. And if so, I got to use that correction factor. Okay, so once you get to doing it, it's one of those things that you're like, and then you get to it, you're like, that's not that hard. It just means if our sample is big relative to the size of the population, we have to put in this extra little factor to correct for it. Okay, pretty easy once you get used to it. Because the idea is, so you know, my little normal distribution thing here, this works because we got like 1,500 BBs in there. Okay, if we only had 10 BBs in there, it would probably not work as consistently. Sometimes it would be like, yeah, we have more in the middle and somewhat to the side. So if our sample is small relative to our population, then the chance of having some error is higher. And so what this does is we multiply this factor. Actually, it takes our curve from being like this to like this, and so when we find like the standard deviation, it's going to be wider. So what we're saying is, in order for us to be certain that this estimate is close, we're going to have to have a wider estimate. Does that make sense? So we're putting error into the system almost to recognize we can't we can't be as certain about this estimate. So in order to say, hey, and we'll get into like how certain are we later, but in order for me to be like 95% certain that the true mean is going to be within this range, I'm going to have to make the range wider. Okay. So that's the idea. All right. So this is to me, this is mind blowing. To you guys, maybe you don't care. I don't know. But most applications, sampling distribution of X bar can be approximated by a normal distribution whenever the sample size is 30 or more. In other words, to me, that's a really small sample. Like regardless of the size of the population, if we have a sample of 30, we can assume it's going to adhere to a normal distribution. And then in cases where the population is highly skewed or outliers are present, we may have to go as high as a sample of 50. That's still incredibly low in my mind. So even like to estimate like how voters are going to vote in the next thing, 320 million, well, that's not our potential voters, that's the total population. Let's say we have 250 million people over the age of 18. A sample of 100 is going to be sufficient for us to make a decent point estimation. Now, if we want to reduce the likelihood of error, we could up that to a sample of 1,000 or a sample of 10,000 or something like that. What's that? Oh, I thought you said something. She's like, no. But so to me, that's kind of mind blowing that even with a sample of 30 or 50, you're going to get a normal distribution. I don't know why it bends my brain, but the math is there. And what we have is this thing called the central limit theorem. And again, if we were in a math class, we'd be like, we're going to prove the central limit theorem. And I'm like, I'll just believe it. You don't have to prove it to me. Like, I'm good. Like my depth of knowledge in this is not really dependent on like a proof. But so let's see. When a population does not have a normal distribution, the central limit theorem will show us that as the sample size gets bigger, it's going to become closer and closer to being approximated by a normal distribution anyway. Again, some math dude way smarter than me figured this theorem out, and it's held true. And so we use it. If you're like, yeah, that's super fresh, then maybe go take major in statistics or something. But to me, that's enough. I knocked over my samples. All right. So here's an example. BEAI employee data. First thing we would do is test, does this have a finite population or an infinite population? So I take little n of 30 divided by big N of 2,500, and I get 0.012. So is 0.012 less than 0.05? Yes. So we're going to call that an infinite population. It does not need to be corrected because the sample is only 1% of the total population, and our threshold is 5%. Okay. So we don't have to do any correction factor. Here's our distribution ends up looking like. It's got a mean of 71,800. It's got a standard deviation of 730.3. Okay. And that units is in dollars, right? Since it was the salary of those people. So this says, so right now, it says, suppose the personnel director believes the sample mean will be an acceptable estimate of the population mean if the sample mean is within $500 of the population mean. What is the probability that the sample mean computed using a simple random sample of 30 employees will be within $500 of the population mean? So now we're getting to the normal distribution stuff you learned in chapter 6. Okay. Pretty easy. We just calculate the z-value of the upper point, 0.68, and then find the probability of that z-value, 0.75. Do it for the lower point. Right, it was plus or minus 500, I think is what he wanted. That comes up with 2.2483. Subtract the upper from the lower. I'm saying we have a 50% chance that given this sample size of 30, that our true mean is going to be within our true population parameter mean is going to be within what the sample comes up with. So if he wants to improve those numbers, he can increase his sample size, right? Because think of the, if you think of the formula for that, the higher the sample size goes, the lower that standard error is going to be. Okay, so that's just what I think what they're trying to distribute to or show you there. And since you already know how to work with norm.dist and norm.s.dist, this is going to be mostly a continuation of that. Okay, so, and I don't know, like, I know Braden was like, to him, that was the easiest part of chapter 6 was the normal distribution parts. And so that's what you said, right? So as we move forward, we're not like, exponential, like we learned about that. That's good. Okay. We're going to be working with normal distribution almost exclusively the next several chapters, which is nice because we know norm.dist, norm.s.dist, norm.inverse. We know those functions now, and we're so comfortable with them that we'll never get them confused with each other. Okay, maybe we will a few times, but it's okay. So again, we use Excel, norm.dist. Remember with norm.dist, we don't have to convert it to its z-score first. We just put in the mean, standard deviation, and the value of x, right? Whereas if we're in standard units, in z's, then we use norm.s.dist. That's the difference between the two. So this is just them working out the exact same thing using Excel function rather than with the math. All right. So here you can see, here it was with an n of 30. This one, the black. And when they up the n to 100, this is now what the distribution looks like. So if we're still looking for the plus or minus 500, it's going to be a narrower range. Okay. And so just recognize that if you're ever like, I want this to be more accurate, all you do is up the sample size. And really what you're doing in real world applications of this is you're trying to balance the cost and time and energy invested in collecting a larger sample size with the increased accuracy you'll get by doing that. And so you're trying to find this like balance, right, of what's reasonable. How close does this estimate need to be? And it depends on the nature of the data, right? If we're looking at, golf scores, and we know that the best golfers in the world are just a hair off from each other, we may have to get some really, really accurate data. Okay. And so it matters. You just have to understand what you're looking for. Okay, I already talked about the relationship between sample size and the sampling distribution. All right, so here's the other two things. So remember I said we have to know if we're doing a finite population or an infinite population. That's one piece of information we have to know. And it's pretty easy because we learned that if our little n over our big N is greater than or equal to 5.05, 5%, we have a finite population. So we have an easy test. And the reason we have to know it is because we have to adjust. If we have this, we've got to do that correction factor. If we don't have to worry about it. So that's the first thing you have to, for any problem you'll be looking at, determine, right? Finite or an infinite population. The second is, are we dealing with a mean, so X bar, or a proportion? Okay. And this is pretty easy to recognize too, because a mean is always going to be like in units of some sort. So like this one, it was in dollars, right? They're salary dollars. But a proportion is always going to be like, it's going to say like what proportion of the people, meaning what percentage of, so it was the case of the management training, right? What proportion of the people had taken management training and which proportion hadn't. Okay. So a proportion is always expressed as a percentage, which is going to be usually presented not even as a percentage, but a decimal between 1 and 0, right? So you have to, so that's the two kind of things for this chapter. You have to be like, am I dealing with a mean or a proportion? And am I dealing with a finite population or an infinite population? So really, there's 4 types of problems you could see. a mean that's finite, a mean that's infinite, or a proportion that's finite, or a proportion that's infinite. And if you can differentiate between those four things, then it's pretty easy to know which a formula to apply to make it happen. Okay, so with a proportion, same idea. A random sample is selected. The sample data provides us a sample proportion, and then we use the sample proportion to make inferences about the population proportion. So here's how you find the standard deviation of a proportion. It's the square root of p times 1 minus p over n. So the proportion times 1 minus the proportion over n, the number of items in the sample. If it's a finite population, it's the finite population correction factor times that. So this little factor, the square root of big N minus little n, divided by the square root of big N minus 1, it doesn't change whether you're working with a proportion or a mean. That correction factor is the same. Okay, just the formula for square root, I'm sorry, for standard deviation is different between a proportion and a mean, and so you need to recognize which one you're working with. Okay. Again, sampling distribution for proportions are approximated by a normal distribution when NP is greater than or equal to 5. So let's go through an example. That'll do better than focusing on it. So for the EAI study, we know the population proportion of employees who participated in the management training program is 0.6. In other words, 60% of the 60% of the employees that for the whole population of employees had participated in the management training program. So what's the probability that a simple random sample of 30 employees will provide an estimate of the population within plus or minus 0.05 of the actual population? Well, first of all, we want to see if it's finite or infinite. So remember, for the finite or infinite, it's NP is greater than or equal to 5. And n times 1 minus p is greater than or equal to 5. If it meets both those conditions, then we're going to say we don't have to adjust. Okay, it's infinite. And then we just set to it this way. The standard deviation, again, that formula is a little different. It's the square root of p times 1 minus p over n. And that gives us 0.0894. That's our standard deviation. Then we can use a mean of 0.6 and a standard deviation of 0.0894, and we can use norm.dist and find the probability of things being there. Okay, so again, this is a little scary, but once you get into it, you'd be like, we've already done normal distributions. Same thing. Okay. Let's see. So I'm going to actually move to just real quick, a little bit more informational stuff. There's other types. So we've talked about random sampling, where we just assign everybody a random number and choose a sample that way. There's other types, and I don't want to spend tons of time on them. But depending on what you're trying to do, sometimes these other types of sampling actually work better for our purposes. So the first one's called stratified random sampling. This is where we separate the group into strata, and then each element of the population belongs to one and only of the strata. So, for example, if we were like, we wanted to survey the population of students at a high school, we could separate them instead of just like taking a random sample of students, we could separate them into strata, freshmen, sophomore, junior, seniors, and then say, in the population, what percentage of the population are freshmen, sophomore, junior, seniors, and then we could interview freshmen, sophomores, juniors, and seniors, get their responses, multiply them by the weights of how their strata is represented in the population, and that may give us a better understanding of the population as a whole. So that's what stratified sampling is, breaking them into some type of strata or group. Cluster sampling is a similar idea where each cluster is representative of a small scale version of the population. So I was talking about that city in Wisconsin or wherever it is. It's kind of a cluster or a representation of the United States as a whole, because they have similar characteristics of the whole population as a whole. And then systematic sampling is honestly, like, you could read that, but I'll tell you, we just use computers to do it. In essence, you take the sample, and then you take a sample of the sample and a sample of the sample, and you run it, you know, 1,000,000 times. This has happened a lot in like sports odds and stuff like that. So they'll take, you know, they'll in essence replay the game 1,000,000 times over. So it's a sample of samples until you've done it so many millions of times that you come out with some reasonable estimate of how likely a given thing is to occur. Okay. I don't, well, you know, I think it's beyond the scope to go any deeper than that into what it is. I don't use it. I don't know. I would probably hire a professional to do that if I wanted to do some type of systematic sampling. And then there's a couple of other sampling types that are not scientific, but sometimes useful. One's called convenience sampling, right? Like, we could just use our students as a sample for, you know, is our new product going to go? And that may not work perfectly, but it's super convenient. We know it may not be as scientific or as a good random sample, but we have the people super available to us. And so we do that sometimes, but that's considered non-probability sampling, meaning we can't make really great inferences based on it. And judgment sampling is another one where we're just going to ask people who are super knowledgeable to make a judgment, right? Believe it or not, they've started finding that judgment sampling, but on large scale, has a ton of value. Like, sort of like crowdsourcing information, right? So it's one thing to ask one person, what do you think the stock market's going to do in the next 5 years? It's another thing to ask 1,000,000 people, and then to take like an average of their responses. They find that it's actually pretty accurate to have, you know, it's like the hive brain is better. So, but again, that's still considered non-probability sampling, meaning they're estimates more than they are sampling. And recognize we're going to have errors in our sampling. Error just means the difference between the value of the statistic and the corresponding parameter, or difference between what the sample provides to us and what the population truly is. Okay. And they occur for all sorts of reasons, including getting skewed samples, including bias built into our questions, right? Like, do you support the terrible, the terrible progressive strategies of this politician? Well, that provides skew, right? Because the person who's like, of course I don't support terrible things. Whereas if you had just like said, do you support this, right? Do you support, or sometimes you'll be like, do you support limiting immigration? And like, in those terms, most people are like, well, yeah, like, we can't just completely let everybody flow into the country without any sort of limit. And then they'll be like, look, all these people are against immigration. Like, well, that's not what I said. So those things are in there. Sometimes they're deliberate, where the person is trying to spin it. Other times it's just like a poorly created question that leads us to conclusions that are skewed. Okay. All right. That's enough for one day. I can see your eyes glazed over. Brooklyn is nearly asleep. I'm sorry, Brooke. I tried to make it interesting, but sometimes it's just statistics. Hopefully when we get into some problems with it, it'll be better. So we will have a guided assignment on Wednesday. And until then, remember who you are. Make good choices. All right. Have a good day.